Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1. Suppose that f of xy has second order Taylor polynomial. G of xy is 5 minus 2x plus 6y plus 3x squared minus 2xy plus 7y squared at 0, 0. Find the values of f sub x at 0, 0, fxx 0, 0, and fxy at 0, 0. All right, now some good news. We're at 0, 0, so they didn't do any weird let's expand and that we might have to worry about. Now there's two ways we could approach this problem. But at the heart of this problem, it's the same philosophy. And that's the following. This second order Taylor polynomial, it's storing the derivatives. In other words, the second order Taylor polynomial is storing the derivatives in the sense that they all match. And not, of course, all the derivatives, but up through the second order. Up through second order. So we can do one of two things. So here's method 1. We can say, look, this 5 minus 2x plus 6y plus 3x squared minus 2xy plus 7y squared is the same as f of 0, 0 plus f sub x 0, 0 x plus fy 0, 0 y plus fxx 0, 0 over 2 x squared plus fxy 0, 0 xy plus fyy over 2 0, 0, I should have said, y squared. And now it's a matching game. Okay, so let's do our matching. So we want fx 0, 0. We say, okay, that's going to be the coefficient of x. And so we come to the conclusion that f sub x at 0, 0 is minus 2. Well, what else do we want? We want fxx at 0, 0. So we say, okay, notice the coefficient of x squared should be, it's 3, or it's fxx is 0, 0 over 2. Okay, so what do? Well, these match. So fxx at 0, 0 over 2 is equal to 3, or fxx at 0, 0 equals 6. And we should mark these here. And now, our last one, we need to find fxy. Well, okay, that's here. fxy is 0, 0. It's the coefficient for the xy term. And so again, matching, we see fxy at 0, 0 is going to be equal to negative 2. All right. There we go. Now, that's one way we could have done it. What's another way we could have done it? Well, the other way we can do it is to say, let's just compute derivatives. And why? Well, because this is storing the derivatives, we have the following facts. Namely, f sub x at 0, 0 is equal to g sub x at 0, 0. fxx at 0, 0 is gxx at 0, 0. And fxy at 0, 0 is gxy at 0, 0. Right? Because they're going to match everything up through the second order. And I realized I missed a couple of things here. Let me just get caught up with all my marking. Okay, so I want to make sure everything's marked up right. Now, so that just says, hey, now, instead of thinking about the problem with f, which I don't know anything about, I just say, look, I just have to do the problem with g, which is given to me right there as a polynomial, so life is good. So we can start, we say, well, what is g sub x? So g sub x is, take the derivative with respect to x, minus 2 plus 6x minus 2y. Plug in 0, 0. G sub x at 0, 0 is minus 2 plus 0 plus 0. So we get minus 2. Gx x. Well, what is that? Well, take the derivative of this with respect to x. What do we get? 6. And when we plug in 0, 0, we get 6. Gxy. Well, take the derivative of this with respect to y. What do we get? Negative 2. Plug in 0, 0, we get negative 2. And there we go. So you can either say, hey, I know what the form of the Taylor polynomial is, match coefficients, probably what they have in mind, but you can also say, look, these derivatives are meant to match. That's how we form the Taylor polynomial. Let's take the derivative of the simple thing and find its corresponding derivatives. It has to match with what we want to find. That's it. And we're done. Woohoo! All right, let's keep going. Use Taylor's formula to find the cubic approximation of the function f of xy is 4 sine 2x minus 3y minus cosine 3x plus y at the point 0, 0. Now, there's one word that's going to make us say like, ugh, and that's cubic. All right, so cubic means up to third order. So we have to compute all of the derivatives up to third order to make this approximation. So to be explicit, we'll write down what we're looking for. So we are looking for the following. We need f at 0, 0, right? That's the 0th order. Then we're going to add in, and I'll switch colors just to emphasize how we're progressing here. And then we're going to add in the first order terms, fxx at 0, 0 times x, and then we're going to add in fy at 0, 0 times y. Okay, those are the first order terms. Now, we're taking advantage of the fact that we're at 0, 0, so it's really x minus 0 and y minus 0. But we say, okay, that gets us to degree 1, first degree. Now we have to get to degree 2. So we say, well, it'd be like fxx at 0, 0 x squared. But in order for our derivative to match, when we take two derivatives with respect to x, we're going to get a 2 coming down. We need to compensate for that, and so we do it by divide by 2. We'll have an fxy at 0, 0 times xy. Now, we don't need to put it in over 2 here, right? Because this is like x to the 1, y to the 1. So every time we take a derivative, well, 1 comes down and a 1 comes down, so we don't need to worry about compensating. Plus fyy at 0, 0, y squared, same thing here. A 2 will come down, a 1 will come down, so we need to divide by 2. Now that gets us up to the second order. And looking at the space I have, I'm going to go to the next line because I need to write down the third order. So the next thing we need to do is we're going to add fxxx. Now that would be xxx, so that's going to be an x cubed. We need to divide. Well, by what? Well, think about derivatives. We'll have a 3 come down, a 2 come down, a 1 come down. So we need to divide by 6. Plus fxxy, 0, 0, and then it'll be x squared y. And what do I need downstairs? I do need something because there'll be a 2, a 1, and a 1. So that's a 2. Plus fx y at 0, 0. X squared, sorry, not x squared, xy squared. Okay, but a 1, 2, 1, so divided by 2. And fy 0, 0. y cubed. And divide by 3 times 2 times 1. Divide by 6. Okay. Now, you might think, great, you're done. No. This is the basic formula for us to fill out. We're only starting. We've only just begun. We have a road ahead of us, my friend. And so I hope you packed a lunch. We might be here for a few minutes. All right, so what's the punchline? We have to compute 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 derivatives. So let's begin. So we have f. So taking the derivative with respect to, well, nothing, right? Just f. Phew. 4 sine 2x minus 3y minus cosine 3x plus y. And f of 0, 0, we can evaluate 0 minus 1. Okay. F sub x. And I should switch colors, so I'm going to do that. Switch to the reddish color. F sub x. All right, going to our next term. So taking the derivative with respect to x, well, derivative of sine is cosine. Bring out a 2. So we get 8 cosine 2x minus 3y. Derivative of cosine is a negative sign, so this will become a plus. And then when we take derivative of the x, there will be a 3. So plus 3 sine 3x plus y. So chain rule. So not the hardest derivatives. So it's not the difficulty of the derivatives. It's the number. All right, so what do we get? Plug in 0. Sine of 0 is 0. Cosine of 0 is 1. So fx at 0, 0 is 8. Now, fy, xy. Well, okay, go back to f and take the derivative with respect to y. Well, okay, derivative of sine is cosine. Negative 3 comes out, so minus 12 cosine 2x minus 3y. Derivative of cosine is, again, negative sign. Now 1 comes out, so plus sine 3x plus y. All right, so that becomes fy of 0, 0, negative 12. Okay, nice. We've already gone through 3, so that's good. Just another 7 to go, and we'll be done. Okay, well, fxx of xy. So come up to f sub x, take the derivative with respect to x. Derivative of cosine is negative sine. 2 will come out, so that makes minus 16 sine 2x minus 3y. Derivative of sine is cosine, and then a 3 will come out, plus 9 cosine 3x plus y. And lo and behold, that becomes, when you plug in 0, so the punchline is whatever's in front of the cosine is what we get. 9. fxy. xy. So I can come up to f sub x and take the derivative with respect to y. Derivative of cosine is negative sine, but a negative 3 comes out. 2 negatives make a positive. So we get a 24 sine 2x minus 3y. Taking the derivative of this with respect to y, derivative of sine is cosine. 1 comes out, and we get a plus 3 cosine 3x plus y. And what will that give us? fxy at 0, 0 is equal to 3. We could have alternatively taken this derivative with respect to x. And notice we get the same thing, right? Derivative of cosine is negative sine. A 2 comes out. 12 times 2 is 24. Derivative of sine is cosine. 3 comes out, so we get a 3. All right. Good. Good. Now, one more. So we go to our next color. Fyy(xy) is what? Well, come to f sub y, take the derivative with respect to y. Derivative of cosine is negative sine. And then we have a negative 3 comes out. And there's already a negative 12. Negative 12 times a negative 3 makes 36 sine. Whew. Except, I forgot my minus sign. Negative 36 sine. Oh my gosh, that's so many negatives. It's such a negative thing here. But yeah, there's a negative there. All right. Derivative of sine is cosine, and a 1 comes out, so we get a plus a cosine 3x plus y. And what's the coefficient? Fyy of 0, 0 is 1. All right. Well, let's keep going. And all right, so now we're into these derivatives. So we're looking for fxxx. Well, come to xx, take the derivative with respect to x. Derivative of sine is cosine. A 2 comes out, so we'll get a minus 32 cosine 2x minus 3y. Derivative of cosine is negative sine. A 3 comes out, so we get minus 27 sine of 3x plus y. And if we plug in 0, 0, fxxx at 0, 0 is minus 32. fxxy. Okay, so we can come and take the derivative with respect to x twice, take the derivative of that with respect to y. Well, derivative of sine is cosine. Negative 3 comes out. That makes a total of 48 cosine 2x minus 3y. And come here, take derivative with respect to y. Derivative of cosine is negative sine. Derivative of the inside is 1. And so we'll get minus 9 sine 3x plus y. And okay, so plug in fxxy at 0, 0 is equal to 48. Now we could have alternatively come to fxy and take the derivative with respect to x. Again, we'd get the cosine, a 2 out, so that's 48. Here we'd have derivative of cosine is negative sine, and a 3 comes out, negative 9. All right, then we can go to fxyy. Okay, so we come to fxy, take derivative with respect to y. And so derivative with respect to y, derivative of sine is cosine. Negative 3 comes out, so that makes a minus 72 cosine 2x minus 3y. And here, taking derivative with respect to y, derivative of cosine is negative sine, and the derivative of y is 1. And so we'll get a minus 3 sine of 3x plus y, meaning fxyy at 0, 0 is negative 72. We could have also come to here, taking derivative of this with respect to x. Notice here, derivative of sine is cosine, and a 2 comes out, giving negative 72. Derivative of cosine is negative sine. Derivative of the inside is 3, so we get a negative 3. There's consistency. That's good. So fyy xy is what? Well, fyy, take derivative with respect to y. Derivative of sine is cosine. Derivative of the inside is negative 3. Negative 3 times negative 36 is 108 sine of 2x minus 3y. All right. Now the derivative of cosine is negative sine. Derivative of the inside is 1. So minus sine 3x plus y. Okay, we're almost there. We're in the home stretch. So fyy at 0, 0 is 108. Okay, now, we're not done yet, but we made it through the bulk of it. the last thing for us to do is to put it all together. Because we have the pieces, this is a generic form, and now we have the coefficients. So we start putting it in -1 plus 8x minus 12y. Then we have 9 over 2, which is also known as 9 over 2x squared, plus 3xy, plus 1 over 2 y squared. Then we come over here, and then we have negative 32 over 6. And, we could simplify that. But in the interest of sanity, I'm going to leave this as negative 32 over 6 x cubed. Yes, I do know that's 16/3. Then we're going to have 48 over 2. And I'll just leave that as 48 over 2 x squared y. Then we have a negative 72 over 2 xy squared. And then we have finally a 108 over 6, which actually that does divide nicely, y cubed. And that, what is the answer? Oh my gosh. Oh my gosh. Now, you might say, hey, that wasn't so bad, right? In principle, no, it wasn't so bad. We could have certainly had much worse. And really the key is just be patient. Be patient and let the process work. And, all right, now you might be saying, is there another way to do this? There actually is. Okay. Just for funsies, right? This is just for funsies, just between me and you. I have another piece of paper here. And it turns out that there's a Calc 2 way to do this problem. And you're like, Calc 2? What? How can you do this with Calc 2? Well, you might remember in Calc 2 we learned about Taylor series. And one of the things you might remember is that sine of x looks like x minus x cubed over 3 factorial plus ... And that cosine of, and actually, you know what? Let me not use x. I'm going to put t. And cosine of t looks like 1 minus t squared over 2 factorial plus ... And the ... is higher order. Now, because these are, ax and by kind of pieces on the inside, we could say, okay, in that case, what we have is that f of xy, we can rewrite it as a polynomial. And as a polynomial, well, this becomes 4 times sine of this piece. Well, this is acting like our t. So we have 2x minus 3y. That's that part, minus 2x minus 3y cubed over 3 factorial plus ... Minus, then parentheses here, we have now the 3x plus y is acting like t, 1 minus 3x plus y over 2 factorial plus ... Now, here's the punchline. These ... terms, these are going to be higher order coefficients. Like, because we want a polynomial, but we only want it up to cubic. So these are going to be parts that we don't need these for our degree 3, so third order. And so, say, so in other words, the answer is what you have here. 4 times 2x minus 3y minus 2x minus 3y cubed over 3 factorial minus 1 minus 3x plus y over 2 factorial. And I can already see, I forgot this square. Okay. Now, you might be skeptical. I understand. let's go ahead and multiply this out and see what we get. So first off, you have the 1 with the minus, so that makes minus 1. This 4 will come through, so then we have plus 8x, right, 4 times 2x, minus 12y. Okay, how are we doing so far? Does it sound familiar yet? All right, and now you're saying, aha, Steve, this is where it's going to break down. Well, 3x plus y squared, you can expand that. That's 9x squared, right? The first term squared. Then you get your cross terms, 6xy, 2 times 3x times y, plus y squared. Now remember, that's all over 2, and there's a minus coming in. So we're going to have a minus 9 over 2x squared. And then we're going to get a minus 6 over 2 xy, and a minus 1 over 2 y squared. Okay. How are we doing so far? Are you convinced yet? All right, hold on. We still haven't got to the fun part, because 2x minus 3y cubed, here's the fun one. If you expand this, this becomes 8x cubed, right? And so, all right, I'll make a little note here to the side. So a plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Just like there's a formula for a plus b squared. Okay, so you get 8x cubed, and now we need a 3 times a squared times b. So we're going to get 3 times 4 times minus 3. Did you get all that? 3 times 4 times minus 3 makes minus 36. And that's going to be x squared y. Now we get 3 times a times b squared. So that's 3 times 2 times 9. 3 times 2 times 9. 6 times 9, that's 54. So 54 xy squared. And then we're going to get this b cubed. All right. And, sorry, just double checking. Yep. B cubed minus 27. So minus 27y cubed. Remember that we're going to multiply by 4, and we also have this divide by 3. It's factorial. So minus, okay, when you do that, I'm going to go ahead and note 4 over 3 factorial. That's 4 over 3 times 2 times 1. That's the same as 2 over 3. So we'll just write it this way. So minus 2/3 times 8x cubed. Then we're going to get a minus and a minus. So that makes plus 2/3 times 36 x squared y. And now we have a minus 2/3 54 xy squared. And finally, a minus and a minus makes a plus. So plus 2/3 times 27 y cubed. All right. And if we clean these up, these coefficients, well, at this point you're probably thinking, this is not any faster. Well, maybe not any faster, but it's another way. That's what I claim. Minus 1 plus 8x minus 12y minus 9/2 x squared minus 3xy minus 1/2 y squared. 2/3 times 8 is 16/3 x cubed. 2/3 into 36. Well, 3 goes into 36. And so that gives us 24 x squared y. 3 goes into 54. That's 3 times 18 is 54. So that's minus 36 xy squared. 3 goes into 27. That's 9 times 2 makes 18. So 18y cubed. Let's compare. We had minus 1 plus 8x minus 12y plus, shoot. Okay, where did I mess up here? I have my signs wrong for some reason. Where did I, minus. Oh, I forgot to do the minuses. Oh, classic Steve. Okay, those were all pluses there. Okay, sorry about that. That's why, do it twice. 9 halves x squared, 3xy, 1 half y squared. Now, 32 over 6 is the same as 16 over 3. 48 over 2 is the same as 24. 72 over 2 is the same as 36. 108 over 6 is the same as 18. So, as long as you don't forget any silly plus sign, this is another way to do it. But I suspect even if you did it and you didn't make a silly mistake like me, your TA would still say, no, you were supposed to do it this way. But, both ways are actually valid. All right, well, that was way too long on one problem. We have so many more problems to do, so let's move on to the next problem. Number 3. Find parametric equations for the normal line to the surface described by the equation sine of 2x minus yz squared plus e to the xy minus 2x plus 4z equals 7 at the point 0, 2, 1. All right, so we're looking for parametric equations for a line. All right, so let's remind ourselves, what does that mean? Well, that means that in particular we're looking for the following, namely x equals, I'll put it as x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. And these are not just random numbers, they were chosen. This part right here, this x naught, y naught, z naught, that corresponds to a point. So this is a point on the line. Now, we actually know a point. It's given in the problem. So we actually can say right away that x0, y0, z0 is 0 to 1. So that part we can fill in. And that's usually fairly straightforward. It tends not to be the point of the problem, right? No, we gotta put in some work, right? So where's the work? Well, it's this piece right here, this ABC. And what does that represent? Well, as a walk down memory lane, this ABC, this is our direction vector. So that's where we're going to spend our time. Okay, so what do we have? Well, notice there was a word we didn't underline yet. Normal. Okay, so what does normal mean? When you hear the word normal in this class, you should think of it as being perpendicular. So this says our line is perpendicular to the surface. All right. Now that's pretty useful. Say, okay, so the direction vector has to be perpendicular to the surface. Now, here we have this surface. What thing is perpendicular to a surface? And that is the fun idea, is if you have this, I'll call it f of x, y, z equals k. Okay, so that's our setup. This long expression here, this is our f of x, y, z. And so we have a level surface in some sense. If that's our setup, then the gradient of f, x, y, z is perpendicular to the surface. So our great aha is we have our function. what we need to do is take the gradient at that point that's perpendicular to the surface. Our normal line needs to be perpendicular to the surface, and therefore the gradient is our direction vector. Okay, so that's how it all ties together. So now we actually just have to do the work. So let's remind ourselves we have our f of x, y, z is sine of 2x minus yz squared plus e to the xy minus 2x plus 4z. So the gradient of f, that's our partial derivatives. So we'll start with taking the derivative with respect to x. Derivative of sine 2x will be 2 cosine 2x. There's no x in that term. There's an x here. Derivative of e to the xy, the y comes down. So that becomes a plus y e to the xy and a minus 2, comma. So this is f sub x. Next, take derivative with respect to y. There's nothing there. Here we get a minus z squared. Here, chain rule, derivative with respect to y, derivative of xy with respect to y, there's an x, so an x comes down. So plus x e to the xy, and that is f sub y. And, because these last terms don't have a y in it, so they go away, comma. Last piece, derivative with respect to z, no z. Here, minus 2yz, no z, plus 4. And this is f sub z. So, with our gradient now in place, we're ready to plug in, and we get the following. Our direction, our ABC, is the gradient of f at our point 0 to 1. So, plug in 0 for x, 2 for y, 1 for z. So 2 times cosine of 0 is 2. 2 times e to the 0 is 2. And 2 is minus 2, comma. Minus z squared, so that's minus 1, plus 0. Once that's 0, doesn't really matter what happens with the e, comma. Minus 2 times y times e, so minus 2 times 1 is minus 4, and then we get a plus 4. So that gives us what? Well, it gives us a 2 minus 1, 0. All right. Well, now we have all our pieces. And we put it all together, and so we get x is equal to 0 plus 2t. So x equals 2t. Y equals 2 plus minus 1 times t. So we'll write that as 2 minus t. Z is equal to 1 plus 0t. So z equals 1. And that's it. That's the process. That's the process. So really, there's a couple things. Understanding what does normal line mean? It means perpendicular. And remembering, hey, how do we set up parametric equations for a line? And then saying, okay, well, how do you find something perpendicular to an implicit surface? We use the gradient. Just like we used the gradient to find our normal vector. So that's also another clue, like gradient's normal vector. The word normal, it's perpendicular. So that helps us figure things out. All right, another problem down. Let's keep going. All right, number 4. Find and classify the critical point, apparently there's just one, of f of xy is 4 log of x plus y minus 4x plus y squared. So this is going to be in 2 phases. So first off, let's focus on the find stage. So in the find stage, we're looking for a critical point. Now, That is, where do we have a place where our gradient is either 0 or it's undefined or there's a boundary. Now, this particular function does have issues because there's a log, but because of the logness, this implies an inherent domain. In the domain, everything's fine. So there's no boundary issues because the boundary is open. That's another story, which we'll get to in the near future. So there's no boundary issues, and there's no undefined gradient issues. So when we talk about find, we're really talking about our classic, hey, the gradient needs to be 0, which translates into two equations. The partial derivative with respect to x is 0, and the partial derivative with respect to y is 0, which says what? Well, take the derivative with respect to x. We get 4. There's a fraction. X plus y goes downstairs. The derivative of x plus y with respect to x is 1. And then minus 4, and that equals 0. F sub y, we have a 4, a fraction again. Derivative of x plus y with respect to y is 1. And then that goes away, and the derivative of y squared is 2y. And that needs to equal 0. All right, so we have our classic two equations, two unknowns. Now, for the first equation, well, what can we do? This becomes 4 over x plus y equals 4, or really this becomes x plus y equals 0. All right, so that's a pretty easy equation. Here, this becomes 4 over x plus y is equal to minus 2y, because you can take the 2y across by subtracting. Or, if we do some cross multiplying, and let's go ahead and, before we cross multiply, we'll cancel a 2 off both sides. We get that 2 is equal to minus y times x plus y. And I don't know why I said x plus y equals 0 up here. It's x plus y equals 1. Momentary lapse. So be careful. Now, this looks like a very complicated set of equations, but actually, notice what happens. X plus y equals 1, right? Here's an x plus y. So, what do you get? If x plus y equals 1, that says, hey, that tells us then that y must be negative 2. All right, well, if y is negative 2, then we can say, hey, x plus negative 2 equals 1. So that tells us that x equals 3. So our critical point, and they were right, there's only one of them, is at negative 2 comma, got to get these in order, is at 3 comma negative 2. All right, so that's the find. We found it. Now, we move into the next phase, and that's the classify. Okay, so for classifying, what's the tool? The only tool we have for classifying is something called the second partials test. So we say, all right, what does that say? Now, the good news is it's written down for us, but just in case, I'll write it down. You compute fxx, fyy minus fxy quantity squared. And then you say, well, there's a couple possibilities. If this is less than 0, then you get a saddle point. It's neither min nor max. If it's greater than 0, well, it's one of two things. If x is positive, you're at a min. And if fxx is negative, you're at a max. If this equals 0, by the way, there's no conclusion. And all right, so that's the test. Now, we have some pieces up here. This piece, this is our f sub x, and here, this is our f sub y. So, we should do some computations. F sub x, taking derivative with respect to x twice, well, this is like 1 over x plus y, and so that's going to give us a minus 4 over x plus y squared. If you're wondering how did you do that, note that, we'll put a little side note up here, 4 over x plus y minus 4 is the same as 4 times x plus y to the minus 1. So when you take the derivative, chain rule, right? The negative 1 comes down, so that's where you get your minus 4. X plus y to the minus 1 minus 2. That's where you get your square downstairs. And times the derivative of the inside is 1, and the derivative of negative 4 is 0. In a very similar way, in fact, almost the exact same way, fxy is negative 4 over x plus y quantity squared. And finally, fyy, well, again, you have your first term, negative 4 over x plus y squared, but then you have just a little bit more. All right, so you have to add plus 2. Now, at your critical point, x equals 3, y equals negative 2, what happens? Well, x plus y is 1, so we get fxx is negative 4, fxy is negative 4, and fyy is negative 4 plus 2. Okay? So, here's our test. We're going to take negative 4 times negative 2, subtract negative 4 squared. Now, we don't need to know the value. What do we care about? We care about the sign. And we say, this is a negative value. So what's our conclusion? We are a saddle. So 3 negative 2 is a saddle. And there we go. We found it, and we classified it. And woohoo! Nice! It's not too surprising that we encounter saddles. Saddles happen pretty frequently. It's a little bit of an interesting problem because most of the time we do these, we see polynomials. But this one had a little bit of a fun twist, a log. And who doesn't love a fun twist? All right. Well, let's keep moving on. Number 5. Find a and b so that the function a times x squared plus 4 times xy plus b times y cubed has a critical point at 2, 4, and then classify the critical point. All right. So it needs to have a critical point at 2, 4. Now that tells us something. It says that if we take our f sub x and f sub y and we plug in 2, 4, what needs to be true? Well, we're going to have to get out 0 because that's the only way we can get a critical point at 2, 4. There's no problems with this being an undefined derivative anywhere because it's polynomial. There's no boundary. So it has to be that. Now, let's make some notes here. What is f sub x? Well, take it with respect to x, 2ax plus 4y. What is f sub y? Well, take it with respect to y, 4x plus 3by squared. All right. Now, we plug in x equals 2, y equals 4. So we get 4a plus 16. And here, we're going to get 4 times 2 is 8. And plus 3b times 4 squared. Well, that's a big number. So let's see, what is that? 4 squared and 7 years ago. Wait, no. That's something else. Okay, 4 squared is 16 times 3 is 48. So 48b. And so we say, hey, this is pretty straightforward. So a would be minus 16 over 4, which makes this a negative 4. And then on the other hand, b would be a negative 8 over 48. Well, 8 does go into 48, so that leaves us with a minus 1 over 6. So our answer for part of this is a equals negative 4 and b equals negative 1 over 6. Okay, so that part's out of the way. We found a and b. But we're not done, because it then says classify it. Okay, so now we have to do our next phase of the problem. Okay, so we're up to our classifying. Now, before we proceed, let's put in what we know. We know a and b. So f sub x really becomes minus 8x plus 4y. And f sub y becomes 4x, and 3 times minus a 6 becomes minus 1/2 y squared. All right, so fxx is minus 8. fxy is positive 4. And fyy is minus y. Now, at our critical point, so our critical point is 2, 4. So at 2, 4, we have that fxx times fyy minus fxy quantity squared. Well, fxx is negative 8. fyy is negative 4. And then we're subtracting this quantity 4 squared. Negative 8 times negative 4, 32. 4 squared, 16. 16. Key is it's positive. All right. Now that we know it's positive, that tells us, hey, you've got something interesting going on. It's not a saddle. What is it? Well, now we say it's either a max or a min. And to figure it out, you look into either fxx or fyy. And remember, we're basically channeling our first, calculus 1 second derivative test, right? If it's positive, it looks like that in the slice. If it's negative, it looks like that in the slice. So, is fxx positive or is it negative? And the same question. They have to be the same sign. So, we see that they're negative. So, it's this kind of curve, which means that if we look in a slice, the slice has that shape. So we are a upside down bowl. We're a maximum. All right, so this is a max. And in fact, we can even be more precise. We can use the word local max. Usually we just say max and that's sufficient. But there's the answer. It is a local maximum. All right. Woohoo! Nice! All right. That was pretty good. Compared to some of the earlier problems, that was fairly straightforward. I like that when that happens. All right. Let's keep going. Number 6. The volume of an ellipsoid is given by, and we have the formula volume ABC is 4/3 pi ABC. Now, if you're wondering where does that formula come from, think of the volume of a sphere. 4/3 pi r cubed. How do you make an ellipsoid? Well, you can start with a sphere and then you just start stretching it. So you stretch in, say, like the x direction, stretch a certain amount in the y direction, and then stretch a certain amount in the z direction. So if you start with a unit sphere, and then you just stretch, say by A in one direction, B in another, C in the third, it scales the volume by those factors of A, B, and C. So that's where it comes from. And, whoops, there's a typo there, where A, B, and C are the axes of symmetry of the ellipsoid. So in other words, it's just like how much did you scale that unit sphere by in each direction. Use a linearization of the volume formula at the point ABC equals 6, 1, 2 to estimate the volume when the ABC is 61 over 10, 6 over 5, and 43 over 20. Now notice 61 over 10, 6 over 5, 43 over 20 are all numbers close to 612. And so that's like a good sign. It says, hey, you're very close. Now, what do we see? Well, is there any key word for us? Well, one key word is linearization. So when we're thinking of linearization, we are thinking of like the flat thing, because that's basically what linearization means. It's the flat thing. We're trying to approximate by a flat thing, like a tangent line or a tangent plane. Now here, it's a little bit fun. There's a fun little wrinkle they've thrown in. It's a function of 3 variables, and that's okay. One slightly annoying thing is that instead of X, Y, Z, near the end of the alphabet, they put in A, B, C. But that's okay. We can handle that. So what's the process? Let's do it this way. So we'll say the linearization of, we'll do it with the symbols that we're comfortable with, and then we'll go into other symbols here. F of X, Y, Z at a point X naught, Y naught, Z naught. Well, it is, you plug in the point F, X naught, Y naught, Z naught. All right. So you have to say, where are you at that point? And then plus, you say, what's the derivative of f with respect to x at x naught, y naught, z naught times x minus x naught? What's the derivative of f with respect to y at x naught, y naught, z naught times how much are you changing with respect to y, plus what's the derivative with respect to z at x naught, y naught, z naught times how much do you change with respect to z. So that's the idea. It's what you think it should be. Now for us, we just have to sort of like, well, get over our uncomfortableness with having the symbols be A, B, and C instead of X, Y, Z. But the idea is the same. And that's the key thing. The ideas remain the same. So if I look at this, we have a couple of basic things to check. So what's the derivative of volume with respect to A? Well, it is, because everything else is constant, 4/3 pi BC. Derivative of volume with respect to B, 4/3 pi AC. Derivative of volume with respect to C, 4/3 pi AB. So for us, this term right here, this would be just the volume. So this would be our volume at 612 plus, and here we would have our partial V partial A at 612 times A minus 6 plus here partial V partial B at 612 times B minus 1, right, because B is 1, plus, in our last piece, partial V partial C at 612 times C minus 2. All right, so that's the linearization. And so that's the punchline. Volume is approximately that. Well, let's do this. What happens when you plug in 612? 6 times 1 times 2 is 12. 12 divided by 3 is 4. 4 times 4 pi, 16 pi. Plus, okay, partial V partial A of 612. So we're now in here. When we plug in A equals 6, B equals 1, C equals 2, we get 4/3 times pi times 1 times 2. So that becomes 8/3 pi. So 8/3 pi, and then times A minus 6. And we're not going to distribute. We're going to leave it as is. Plus partial V partial B at 612. So we're plugging in A is 6, B is 1, C is 2. So we get 4/3 times pi times 6 times 2. All right, well, 6 times 2 is 12. 12 divided by 3 is 4 times 4 pi, 16 pi. So 16 pi, B minus 1. Partial V, partial C, 6, 1, 2. Okay, again, A equals 6, B equals 1, C equals 2. So you get 4/3 times pi times 6 times 1. All right, well, that's 4/3 times 6. And 3 goes into 6, so that's really 4 times 2. That's 8. Okay, so we get plus 8 pi times C minus 2. All right, that's the linearization. Now notice the problem didn't ask us to find the linearization. It asked us to use a linearization. So, all right, so what's the last thing for us to do? Well, now that we've found it, we need to use it. How do we use it? We plug in. So our volume at 61 over 10, comma 6 over 5, comma 43 over 20 is approximately 16 pi plus 8/3 pi times 61 over 10 minus 6 plus 16 pi times 6 over 5 minus 1 plus 8 pi times 43 over 20 minus 2. And we can clean this up. Well, what is that? That's 16 pi plus, we have 8 over 3 pi. Now, here, this 6 is what? Well, we can write it as 60 over 10. And so we have 61 over 10 minus 60 over 10. So that's times 1/10. Plus, we have 16 pi. And here, 6 over 5 minus 5 over 5. So times 1/5. Here, we have 43 over 20 and minus 40 over 20. So plus 8 pi times 3 over 20. But we can go even further, right? Here, I see there's a factor of 2 in common, so I can put a 5, and that leaves you a 4 up here. Nothing in common here. 8 and 20, that has a factor of 4 in common, so 2 and 5. And so, what do we have? Well, we have 16 pi plus 4 over 15 pi plus 16 over 5 pi and plus 6 over 5 pi. Now, what would we want to do? Well, we'd want to add these all up, right? No problem. We can do that. We just need a common denominator. What's the most common denominator here? It's 15. All right, so 16 times 15 is, altogether now, 240. Very good, very good. All right, so this is 240 over 15 pi plus 4 over 15 pi plus 48 over 15 pi plus 18 over 15 pi. Okay, and if we add these numbers up, 18 plus 48, that makes 66, I believe. Does that sound like a real number? Yeah, it sounds like a real number. So that's 66 plus 4 makes 70, plus 240, that makes 310 over 15 pi. But we can simplify that, because these have factors of 5 in common, right? So if we pull out a 5, that makes a 3 downstairs, and here that makes 62. So this gives us 62 thirds pi. Whew! Done. Done. All right. Well, that's the answer. So we see that we got an estimate of 62 thirds pi. Now, is this reasonable? Well, we're comparing it to 16 pi, and how does that compare? Well, it's bigger. 16 pi is 48/3 pi. And you'll notice we stretched in each direction. So yeah, that's a pretty reasonable answer. And there you go. There you go. All right. Well, nice ideas here. And I think that the nice idea here is, hey, practice linearization for more than 2 variable inputs, like for 3 variable inputs. And by the way, it works for any number of inputs. It's the same process. All right. On to our next problem. Number 7. Consider the surface S defined by the equation x cubed plus 3x squared plus y squared minus 4y plus 6z equals -7. Find all the points, all of them, so that the vector v equals 3, 2, 2 is a normal to the tangent plane to S at P. All right. Good. Well, we know what setting we're in because there's a big clue in the way that they write the problem. Now, they could have written this as z equals, but they chose not to. And so we'll embrace their choosing not to. And so they said, okay, we have this f of x, y, z equals k. So f of x, y, z equals k. Then the normal, or did I misspeak there? Spoilers! The normal is the gradient of f of x, y, z at that point. Okay. So, well, let's figure out what does the normal look like. We say our gradient, that's our collection of partial derivatives, and that looks like the following. Taking the derivative with respect to x will give us 3x squared plus 6x, comma. Taking the derivative with respect to y would give us 2y minus 4, comma. Taking the derivative with respect to z would be 6. All right, now, this is our typical normal. And we say, okay, but what do we want our normal to look like? Well, we want our normal to look like 3, 2, 2. Now here's where we're like, this is not looking very 3, 2, 2 like. Uh-oh, Steve, we're in trouble. Or are we? So I used a word a few moments ago, the normal. That was the wrong word. I misspoke. Normal. Normals are not unique. And so, what's true? You can always scale a normal by any non-zero number. You still have a normal. Because the important thing is the direction. The scaling doesn't change the direction as long as you don't multiply by 0. And so you say, oh, okay. So the gradient has to be some multiple of the vector 3, 2, 2. Now, what we have to do is figure out which multiple. But this will be a little bit more straightforward than you might think, because it says, hey, a normal has to look like 3k, 2k, 2k. And now we just start matching. And we're like, oh, cool. So we have now a series of equations. There's actually 3 equations and 4 unknowns, right? X, Y, Z, K. But you'll notice that the Z has gone away. So that's going to make things a little bit simpler. So we need to have 3x squared plus 6x. That needs to equal -3 times k. We need 2y minus 4. All right, that needs to equal 2 times k. And we need that 6 has to equal 2 times k. Now we say, well, that helps simplify things. K has to be 3. All right, well, let's plug that into these other equations. And what does that give us? Well, it gives us two things. Let's do the y equation first because it looks simpler, and I'm a fan of doing simpler things. We get that 2y minus 4 has to be 6. That becomes 2y equals 10. We can add 4 to both sides. And that becomes y equals 5. Okay, so that's great. Y has to be 5. Now, let's go to our first equation. We plug in k equals 3. All right, what does that give us? Well, it gives us 3x squared plus 6x equals negative 9. Now we can move that across, or 3x squared plus 6x plus 9 is equal to, why did I say negative 3k here? This is positive 3k. I am so sorry. I don't know why I put negative 3k there. So this is a plus 9. This is a minus 9 equals 0. Or divide by 3, x squared plus 2x minus 3 equals 0. And now that factors. Factors as what? X plus 3, x minus 1. So we get x equals negative 3 or x equals 1. All right. Now, what do we know? We know our x value can be one of two things, and our y value is determined. So we have 2 points, negative 3, 5, something, 1, 5, something. Now, is that our answer? Well, it will be as soon as we figure out what's the last piece, right? Because we need a point P, and P has 3 entries. It tells us x, y, z. We were able to solve for the x's and the y's. We got 2 points. We haven't yet figured out the z yet. Where do we get the z from? It's not anywhere in here. There's no z. So where do we get it? And the answer is we go back to the original formula. So let's see what happens. When we plug in our point, we can do 1, 5 first. At x equals 1, y equals 5. What goes on? We're going to get 1 plus 3 plus 25 minus 20 plus 6 times z equals negative 7. Well, 25 minus 20, this makes a 5. Plus 1 plus 3 is 9. And, okay, so we're going to subtract that, or 6z equals minus 7 minus 9 would make that a negative 16. So what do? We can divide. All right, so divide both sides by 6. So z is negative 16 divided by 6, which we can take out a factor of 2, negative 8/3. So that gives us our last entry here, negative 8/3. And I'm a little bit paranoid here, so I'm just going to double check. Plugging in x equals 1, 1 plus 3, y equals 5, 25 minus 20, yep. And yeah, that's all. That's good. All right, now do the same thing at your other point. So at x equals negative 3, y equals 5. Well, we get negative 3 cubed is negative 27, plus 3 times negative 3 squared, which is plus 27, plus 5 squared, 25, minus 4 times 5, so minus 20, plus 6z equals negative 7. Well, the 27's cancel. Here we have a 5. Subtract. this becomes, or 6z is equal to minus 12, which says z should be minus 2. So we get the 2 points. Minus 3, comma 5, comma negative 2, 1, comma 5, comma negative 8/3. All right. And those are our 2 points. Woohoo! All right. Good. Good. And let's keep moving on. Number 8. Use a directional derivative to approximate the amount by which the function, we have an f of x, y, z is 2x minus x sine z plus 3y cosine z plus 4z changes when moving from the point P0, 1, 2, 0, a distance of ds is 0.3 units towards the point 7, minus 1, 2. Okay, so what's happening here? Well, what's happening, if we think about our setup here, now we'll talk about the ds in just a moment here, but we're at a point P0. So we'll mark our P0. We'll say P0 is here, and we're going to head towards P1. And so we have a direction, because if we have 2 points, we can talk about, well, we start at one and we move to the other. That's the direction. Now, it's not the direction vector. We got to make that a direction vector. What this says is we're going to move part of the way. So ds is a small amount of distance. So we're not going the whole way, but we're just going 0.3 units in that direction. Now, how do we get our answer? Well, what this is this is the amount of change. And then we have a rate of change. So the derivative is the rate of change. The ds is the amount of how much we've changed. How much we've changed our input by. So what we're going to get is that our change in output, which is really what we're after, we're approximating the amount by which the function changes. The change in output is approximately, and I'll explain why I use the word approximately here. Part of it is it says approximate, but we'll also explain why it's an approximation. You find the directional derivative at that point, and then you're going to times it by 0.3. So this is your rate of change, and this is the amount of change of the input. All right. Why is this an approximation? Well, because 0.3 is not, infinitely small is really the issue. And even 0.3, a lot can happen in 0.3. So there's going to be a very small amount of error. But, of course, the smaller this number is, the better this approximation gets. That's the whole punchline. So what's our problem about? Well, now that we know what to do, it's really saying, hey, you need to compute this directional derivative, and then you need to times it by 0.3. Ah, okay. That we can do. So recall that if we're computing the directional derivative of a function at a point, then this is found by taking the gradient of the function at that point, dot u. So we have 2 tasks ahead of us, the gradient and u. But for that, the u, I'd like to do that because that tends not to be too bad. Here we're going from P0 to P1. So start by saying, well, let's look at our change. So if I look at this vector from P0 to P1, I say, well, how much do I change in each entry? I go from 1 up to 7, that's a plus 6. I go 2 to negative 1, that's a negative 3. And I go from 0 to 2, so that's a plus 2. So a 6, a minus 3, and a 2. Well, all right. Now with that, I want to find the magnitude of this vector. So that's the square root of 6 squared negative 3 squared, and 2 squared. Well, that's 36 and 9 and 4, or 49. The square root of 49 is 7. Okay, so that makes 7. Now, what is u? U is 1 over 7 times 6 minus 3, 2. Okay, so that's a part of our computation. That's our dot u. Now we have to find our gradient. All right, well, no worries. We've done these kinds of computations before. So the gradient of f, well, take the collection of partial derivatives. Derivative with respect to x, 2 minus sine of z, and that's it, comma. Take derivative with respect to y, 3 cosine z, and, oh, that was pretty quick. Take derivative with respect to z. Derivative of sine is cosine, and so we're going to get a minus x cosine z. Derivative of cosine is negative sine, so minus 3y sine of z, and then we'll get a plus 4. All right, we need to plug in our point. So the gradient of f at 1, 2, 0. Now, sine of 0 is 0, so that first entry is a 2. Cosine of 0 is a 1, so that next entry is a 3. Cosine of 0 is a 1, so there's a minus 1. All right. Sine of 0 is 0, so that goes away, and a plus 4. So that makes it a 2, 3, 3. All right. So we now put these two pieces together, and we say, all right, their powers combined, they are the directional derivative. So our dufp is 2, 3, 3 dot 1/7 6 minus 3, 2. All right, that's 1/7 times 2 times 6 is 12. 3 times negative 3 is minus 9. 3 times 2 is 6. Yes, I think. Let me double check. 12 minus 9 plus 6. Okay, yeah, math checks out. 12 minus 9 is a 3. And if you add 6, that's a 9. So we get 9 over 7. Okay, now that's not our final answer. That needs to be times by 0.3. So our estimation for the amount by which the function changes. So we take 9 over 7 times 0.3, which, by the way, is 9/7 times 3/10. We can write it that way. We end up with 27 over 70. And nothing in common. So there's the answer. That's the amount of change. That approximates. It's an approximation to how much the function will change as we move in that direction. All right. There we go. Woohoo! Nice. Nice. So it's basically understanding, hey, what does this ds mean? It's basically a change in length. So we've moved a distance. So even if the ds wasn't there, it just says, oh, we've moved a distance. And so it's like, oh, okay, so we've changed our inputs by that amount in that direction. All right. Good. Good. All right, let's keep going. Number 9. Find and classify the 3 critical points of g of xy is 3x squared y minus 2x cubed plus 3y squared minus 24y plus 11. So we know we better find 3 of them because it says there's 3 of them. All right, well, okay, so there's 2 stages. We have to go through the find stage, and then we've got to go to the classify stage. And I like to start with the find. So let's work on the find. So for the find process, this is saying, hey, we need the gradient of g to be 0, which really says we need 0 equal to g sub x and 0 equal to g sub y. Well, what is g sub x? Take the derivative with respect to x. We get 6xy minus 6x squared, and that's what we get. All right. G sub y, what do we have there? Well, we get 3x squared plus 6y minus 24. All right, great. Now, two equations and two unknowns. But these are sort of fun two equations and two unknowns, or more like, these are devious two equations, two unknowns. Let's start with this first one. Notice here they have something in common. Let's pull out their common terms. So this becomes 6x times y minus x. Now, what does that tell us? Well, notice it equals 0. So it tells us that there's really two paths that we could be taking. Two roads diverged in a mathematical wood. One is that x equals 0. The other is that y minus x equals 0, or y equals x. Let's suppose we go down this path. The path that says x equals 0. We haven't come to this equation yet, but now that we know x equals 0, the second equation tells us that 0 has to equal 6y minus 24. Or, if we move the 24 across, 6y equals 24, or y equals 4. So this leads us to a single point, 0, 4. All right, so there's 1. We need 3, so let's see. Hopefully this gives us 2. Now, we're told y equals x. So what does this give us? Well, I can replace y by x. So this gives us 3x squared plus 6x minus 24 equals 0. Okay, well, we can factor 3 out. That comes x squared plus 2x minus 8 equals 0. And that factors even more. So how does that factor? Well, we need two things to multiply to negative 8, but add to positive 2. For example, x plus 4, x minus 2 might do it. Let's check. X squared, good. Minus 2x plus 4x is 2x, and minus 8. So that says, aha, x is 2 or negative 4. So that leads us to the point 2. And remember, y is 2, so 2, 2. Or negative 4 for x, but y is also x. So that leads us to negative 4, negative 4. 1, 2, 3. Nice. Woohoo! We found it. We found our 3 points. Time to celebrate. But just a moment, because we gotta go to our classify. Okay, so for classifying, we have to do our computation. We need to figure out what's gxx times gyy minus gxy quantity squared. This is sometimes called d, not to be confused with d for derivative. This is more the d for discriminant, but that's a different story. But anyways, we have this quantity here. Now let's compute these partial derivatives. We have g sub x written down here. So gxx would be 6y minus 12x. Gyy, come here, will be 6. Gxy, well, if we take the derivative of this term with respect to y, or take the derivative of this term with respect to x, either way, you get 6x squared. All right, now we need to test these at these 3 points. All right, so at 0, 4, we get that this value d is, well, x equals 0, y equals 4, so we get 24 times 6 minus 0 squared. Well, that's a number. It's 144, but we don't really need to know that. We just need to know the sign. It's positive. We also can see that these pieces, the gxx and gyy, they're also positive. And so remember that when we're positive, it's a min or max. Look in a slice and apply the second derivative test from Calc 1. Or you could just say, hey, there's the formula that says, look, d, which is this quantity, gxx gyy minus gxy squared, if it's less than 0, saddle. If it's greater than 0, break it up. Gxx positive min, gxx negative max. If it equals 0, no conclusion. All right. So we'll add a note, and gxx, really, gyy is always positive, but gxx is positive, so that means a min. All right. We'll summarize this all in a minute. At 2, 2. Well, what's happening here? Well, we'll get 12 minus 24. Negative 12 times 6. Subtract 6 times 2, which is 12 squared. That's minus 72. Subtract 144. That's negative. Negative value, saddle. All right. And at minus 4, okay, what's going on here? So we plug in x equals minus 4, y equals minus 4. We get negative 24 plus 48, right? Negative 24 plus 48. So that makes a positive 24. And then we have 6, subtract, and then 6 times negative 4 is negative 24 squared. Now, do I know this number off the top of my head? Probably not. You know, who remembers 576? Nobody remembers that. But I don't need to remember that. All I have to say is which one's bigger. And I say, well, 24 times 6 versus 24 times 24. The 24 times 24 is bigger. And I'm subtracting the bigger thing. This is negative. So, also a saddle. All right. Good. You might say, what's good about it? Well, what's good is we've done the classifying. So let's put it all together. And so we have our critical points. We have, make a list, 0, 4, which we can say local min. We can just say min. We have 2, 2, which is a saddle. And we have negative 4, which is also a saddle. And there we go. All right. We did it. Woohoo! Yay, us. Good job, team. Good job, team. All right. We still have one more to go. So let's finish it up. Number 10. Suppose that g of xy is a function having second-order Taylor polynomial. P of xy is 4 minus 2x plus 5y plus x squared minus 3xy plus 2y squared at negative 1, 1. Find the linear approximation to g of xy at minus 1, 1. All right. Now, what's tempting? We're like, hey, here's the Taylor polynomial. Now, linear approximation, we know that. That's just another way of saying a couple of things. Linear approximation has a few names. It's also known as tangent plane. But it also has one other name, which we probably haven't said explicitly. We've said implicitly. It's a first-order Taylor polynomial. And now you're like, this is going to make this problem like super-duper easy, isn't it? Because what can we do? Well, we have the second-order Taylor polynomial, so it must have the first-order Taylor polynomial inside of it. So it must just be super clean, right? Can't we just like hey, here it is, and that's it? Walk away, drop the pen? No, we can't do that. There's more to be done. All right, so there's no pen drop here. What's the issue? What's the subtlety? The subtlety is right here. Notice that they said at minus 1, 1. So that says the way that we should have written our Taylor polynomial, we should have had terms that look like x minus minus 1, which is x plus 1. And we should have also had terms that look like y minus 1. So notice they don't. They have x's and y's, which means somebody came through and said, oh, let me expand. They expanded. Why? Why? Why did you do that? Okay, all right. So that's why we can't describe the first part. Because somebody came through and expanded. And as they expanded, that affects the lower pieces. All right. We're back in our column space. So what do? Well, we say, okay, if we're looking for the linear approximation, and we are, that hasn't changed, we say, well, what information do we need? So we need the following. We need to get what is g of 0, 0. What is g sub x at, sorry, not 0, 0. Got distracted. G at negative 1, 1. G sub x at negative 1, 1. And g sub y at negative 1, 1. And here's the good news. The Taylor polynomial has stored that information. Even though they obfuscated it by expanding, it's still there. And we don't have to think hard to find it. We just say, well, that says because everything has to match up through second order, it definitely has to match up through these. So this is the same as p of minus 1, 1. P sub x at minus 1, 1. And p sub y at minus 1, 1. Well, let's go ahead and get this one out of the way. So we're plugging in x equals minus 1 and y equals plus 1. So that's 4 plus 2 plus 5 plus 1. And minus 3 times minus 1 times 1 is plus 3 and plus 2. 4 plus 2 plus 5 plus 1 plus 3 plus 2. There's a lot of numbers in here. But if we add all those up, 6, 11, 12, 15, 17. All right. So that's g of minus 1, 1, which is p of minus 1, 1. All right, good. We need two more terms. We need g sub x and g sub y. Well, for those, we'll compute the partial derivative. So p sub x of xy, we'll write that down here. Take derivative with respect to x, we get negative 2 plus 2x minus 3y. And while we're at it, in the derivative mode, we'll do p sub y. So derivative with respect to y, we get 5 minus 3x plus 4y. All right, so p sub x at minus 1, 1 is minus 2. Minus 2, right? Because x is minus 1. And minus 3. Lots of minuses going on here. Minus 2, minus 2, minus 3 makes that minus 7. G sub y at minus 1, 1. That's p sub y at minus 1, 1. So that's a 5. Minus 3 times minus 1 is a plus 3. And a plus 4. That makes 12. All right, good. So we have all the pieces in place. Good for us. Now we just have to put it together and we're done. We're done. All right, well, so our linearization is g of minus 1, 1 plus g sub x at minus 1, 1 times x minus minus 1, x plus 1, plus g sub y at minus 1, 1 times y minus 1, which makes it 17 minus 7 times x plus 1, and then plus 12 times y minus 1. And there we go. Now, we could call it a function if we want, L of x, y, but we're amongst friends. We know what we mean. All right, we made it through. All right, so this one, lots of stuff about Taylor polynomials on this particular quiz, and they are beautiful tools. They're wonderful tools. Just remember what's happening with the Taylor polynomial. We are trying to approximate the function, and we're doing it by storing derivatives. We also had a few other ideas, a little bit with using gradients, directional derivatives, finding tangent planes. We also did some finding critical points, classifying critical points. So it was a good workout. We definitely had a good, challenging time. Lots of these problems, there's lots of little pieces, so be careful. It's easy to make mistakes. I've made a couple of mistakes. Check your work, and oftentimes you say, there's a small mistake. So as the great mathematical philosophers would say, you should check yourself before you wreck yourself. Thank you for coming and joining me, working through and doing problems with me. I am grateful for all the work that you're putting into this. You are capable. You are able to do this. Work at it. It will come. I believe in you. I hope to see you again. Take care. Bye.